Uh, so today I'm going to give you a talk on machine learning applications for 5G and 6G wireless communications. Many of you may be knowing this already in many Western countries like USA, Europe, in all, even in China, they started deploying 5G. In 2020 itself, many of the countries started deploying 5G. Uh, they are aiming for 6G in 2030. Okay, now applying the concepts of artificial intelligence and machine learning for wireless communication. That is that the topic is hot research topic. We recently started working on machine learning applications for 5G and 6G wireless communications. I just want to share uh, some of my understandings in this presentation. I'm going to start with supervised learning. Supervised learning. The theory behind supervised learning, what is the signal processing concepts associated with this, and where it is exactly used. Okay, few applications I will point out. Again, in supervised learning, other than regression, I will consider binary classification, again where it is used. Then, if time permits, I will cover unsupervised learning. For all these machine learning uh, applications, I will just relate some of the 5G 6G key technologies. This is what the outline of my presentation. So many of you, those who are working in wireless, you might have seen this particular wheel. This is actually the comparison between 4.5G long-term evolution advanced and fifth generation, okay, 5G new radio. So the outer wheel, that is the key requirements of 5G, whereas this inner wheel, okay, that is the support provided by the present 4.5G. So I'm not going to cover all the aspects. So for example, how you can understand this particular will, say in the case of LTE-A, it can offer a peak data rate under ideal conditions. It can offer a peak data rate of 1 gigabits per second, whereas in 5G, the demand is 20 gigabits per second. So like that, you can compare each and every parameter and you can understand what is the key requirements of 5G. I'm going to focus on this particular aspect. Okay, so here machine learning plays a major role. If you notice, in 4.5G, okay, it is expected to offer a latency of 10 milliseconds. It is expected to offer a latency of 10 milliseconds. Whereas now in 5G, okay, the end-to-end latency, that is 1 millisecond. Okay, so this is very important. So the algorithms, the hardwares, whatever you are developing, there should be no hardware complexity. There should be very less computational complexity. Then only you can achieve this. Okay, here actually machine learning plays a major role. That is what we are going to discuss. One more point I want to tell. So up to 4.5G, people are discussing only about this enhanced mobile broadband. That means they need very high data rate. Okay, the data rate is not sufficient, so they are aiming for very high data rate. So the concepts like the technologies like MIMO, carrier aggregation, multiple radio access technologies, all those things come here. But 5G is not only for enhanced mobile broadband. There are other two use cases of 5G. One is massive machine type communications. In other words, I can say Internet of Things or wireless sensor networks. You have uh, you have several low power sensor nodes deployed throughout the monitoring region. Okay, so if you notice here, data rate is not important, but the battery power, that is very, very important because sensor nodes are battery operated. Other than this, here you can see ultra reliable and low latency communication. So here if you see, I'm not going to bother about the data rate, I'm not going to bother about the battery, but latency is very, very important here. Okay, so for example, you might have heard about autonomous cars, unmanned aerial vehicles, in all those things. So driverless cars. So say suddenly a person is crashing, you have to control immediately. So within this 1 millisecond or something, the communication has to reach the car or the vehicle, and it has to stop immediately. So the latency is very, very important. Industrial automation, so their latency plays a major role. Okay, for these use cases, latency is very, very important. So this entire talk, actually, I'm just focusing, we are going to use machine learning algorithms, okay, to reduce the latency. Okay, that is what my presentation is. So even the previous speakers, they might have introduced this particular block diagram. So in machine learning, we have to fit a model. That's very important. We have to fit a model. So how we are fitting the model? For that, you need a data set. Okay, you need a data set. So usually what we'll do, we'll pre-process the data, we will clean the data, we will remove the outliers, we'll remove the missing data. So all those things we'll do here. We are not going to discuss much about this. Then, given the data, we are going to extract the features. Given the data, we are going to extract the features. If it is supervised learning algorithm, for each sample, okay, you have features and you also have the labels. Okay, you also have the labels. If it is unsupervised algorithm, we don't have these labels. That we'll discuss one particular application at the end. So from the data, using feature extraction, we have to extract the features. Okay, once the feature is ready, using some machine learning algorithm, you can develop a model, you can fit a model. Okay, then we have to validate the model. There are different techniques available for validation. Say for example, if it is a regression kind of thing, we have the metric like mean square error, root mean square error, all those things. If it is a classification problem, accuracy is the metric. Like that, we can use some metric. If we are not getting the desired performance, then we have to improvise the model. So what we are doing, we can clean the data, or we can use better feature extraction algorithms. So all those things will go for the better model. So once the model is ready, okay, for example, say I have only two features, something like this, and we got a model like this. Okay, say if the new data point falls above this line, say let me call that as +1. If it falls below this line, let me call this as -1. So what I will do, when the new data, this is basically done with the offline data. Okay, offline data. Whereas this testing phase or the prediction phase, that is done with the online data. When the new data comes, already we trained the model. So where it is, where is the location of the new data? If it is above this line, I'm going to say it's +1. Otherwise, I'm going to say it's -1. This is a binary classification. So we have multi-label classification, all those things. So this is how the machine learning algorithms works. So let me start one of the application of supervised learning, linear regression. Okay, we have the data set. Wherever required, I'm going to use signal processing concepts and mathematical concepts. Mathematics is unavoidable here. So we have the data set. Okay, for example, say you have the data set which contains age of the car, okay, how many kilometers it has run. For example, what is the fuel type, whether it is a petrol car or a diesel car or CNG, okay, what is the corresponding price. So this is the used cars details, okay. So if you notice, I may have like that, I may have some thousand different cars data. So age, kilometer, fuel, what is the price. So age, kilometer of these are samples. Basically these are samples. How many samples or records I'm considering. I'm going to use small m to represent the number of samples. I'm going to use d to represent the number of features. These are called features. This is called label. Okay, this is called label. uh, so if you see this feature, that's basically a vector. Okay, this feature is basically a vector. Suppose if I write x1, okay, that is the feature vector of first sample. Okay, the feature vector of first sample, you can see I used a bold here, whereas the price, that is scalar. Okay, so it has three values, x1 1, x2 1, x3 1. This one indicates sample index. This 1 2 3, they indicate a feature index. Okay, why I am using to represent the label. Okay, so you can understand whatever I have written here. There are m records. Okay, there are m records and there are d features. You have the label, so basically it is a supervised learning. So what we are going to do, we are going to train a model. We are going to train a model using this data set. Okay, if if a new feature set is given, I should predict, okay, the corresponding label. Okay, so before doing this, I need to construct a model. So usually what we do, we find out the regression coefficients. Regression coefficients means I'm going to multiply first feature with some weight, second feature with some weight, third feature with some weight. Okay, I'm going to formulate the linear equations. I'm going to solve the linear equations. If I know W1, W2, W3, so given the new test data, okay, I'm not writing test every time. Uh, this is scalar. Each feature is scalar. So given the test feature, I'm going to multiply this with W1, I'm going to multiply this with W2, I'm going to multiply the third one with W3. If I add everything, I will get the approximated, or the predicted, not approximated, the predicted price. So this is what the idea of linear regression is. So you can see the same, whatever I conveyed now, that mathematically I have represented. So this is first sample. This one indicates first sample. These are, this is feature index, first feature, second feature, dth feature. So I'm multiplying first feature with W1, multiplying second feature with W2, dth feature with WD. These are some noise. Okay, in communication you can consider this is noise. Always you don't the data set whatever we have, that's not exactly correct. Whoever observing the data, he might have entered some wrong data, all those things. So this is the first label. Similarly, see, I have written this, okay, in a vector form, something like this. I have written this in a vector form. Same way, second sample, uh, m sample, okay. So if you combine all these things, you will get this particular expression. For example, I will write, we have this equation, we have this equation, we have this equation. So left hand side it is y1, y2, ym. Okay. Right hand side, this is x transpose 1, X transpose 2 by that X transpose M, and you have W vector plus epsilon 1, epsilon 2, epsilon M. So basically this is a vector of size M by 1, M rows and 1 column. This is also a vector M by 1. Okay, so if you look at this, each one is a vector, each one is a row vector. So there are m rows, and each feature vector that has d features. So this is basically a m by d. Okay, so you can see the dimensions were written. So same thing was written here. So y is equal to yeah, x is the matrix. This is a vector. X is matrix. W is the vector plus epsilon. This is also a vector. So if you look at this, I just took 3 features, but the number of samples, they are 1,000 samples. Okay, the number of records available, that is more. So in linear algebra, so our objective, as I said earlier, our objective is we have to find out these weights. We have to find out these weights. How do you find out these weights? So you have 1,000 different linear equations. You have to solve all these 1,000 different linear equations. That is very difficult. But in linear algebra, we have the solution. So this we have 1,000 equations because the size of y vector is 1,000. We have only 3 unknowns. W1, W2, W3. We have 3 unknowns. So the number of equations more than the number of unknowns. This problem in signal processing they say as over-determined system. If you have the number of equations and the unknowns, they are same. It is very easy to find out W vector. So what you do x inverse y, you will get W cap. But this x is not square. Okay, so we have to go for over-determined system. So the solution for the over-determined system that is already available in the linear algebra, that's called least square solution. So this is how you can calculate the unknown weight vector. So once you know the weight vector, whatever the new test sample is coming, new online data is coming, you can weight each feature based on this W and you can predict the price. Okay, so this basically one more thing I want to point out, this is actually not the exact inverse. This is called pseudo inverse. Okay, I'll write that here. X transpose X inverse X transpose. Why this is pseudo inverse? For example, I will write this X transpose. If I multiply this with X, what happens? X transpose X inverse X transpose X. You see, whatever available here, same thing available here with inverse. So you will get identity matrix. So this is basically called pseudo inverse or left inverse. Okay, not exact inverse. Next one, there are cases that you may have less number of features, say 100, less number of samples. You may have less number of samples, but you may have more number of features. For example, say 50,000 features are available. 50,000 features are available. In that case, if you see, the number of equations are less than the number of unknowns. The number of equations are less than number of unknowns. So again here we go for over-determined system solution, that is called least norm solution. So this is how you can calculate the unknown weight vector. Okay, again the solution, we are just taking the fundamentals from linear algebra. This is what the solution is. So earlier for least square I said left inverse, now it is right inverse. So this is our pseudo inverse. X dagger is X transpose, X into X transpose inverse. So what I will do, uh, X into X pseudo inverse. So right hand side also I'm just adding X. So if you see whatever available here, same thing is available here. So this results in identity. Okay. So this is basically a right inverse. You are getting the inverse by adding this in the right side. Whereas in the previous case, you are getting the inverse by adding this pseudo inverse in the left side. So this is called a right inverse. Okay, so three different solutions from linear algebra. If the number of equations and the number of features, number of equations and the number of unknowns, they are equal, we can go for inverse, because for square matrix and full rank matrix, inverse exists, so you can do inverse very easily. Otherwise, either you go for least square solution or least norm solution. Okay, if you get the W vector for, if you get the W vector for the new online test data, okay, for the new online test data, you can multiply. Okay, first feature you multiply with W1, second feature you multiply with W2, like that you have D features. Okay, you will get Y test, you can predict the value. So where this is exactly used in wireless communication. Okay, for example, this is a massive MIMO system. You can see there are k number of users, and there is a base station with plenty of antennas. There is a base station with plenty of antennas. So let me consider uplink communication. Uplink in the sense so the users are the transmitters, base station is the receiver. So you can see only one antenna, or you just consider there are two antennas in the transmitter, and there are 100 antennas in the receiver. Okay, so usually y vector is h into x vector plus n vector. You can just this is similar to the expressions whatever we developed, x into uh, x into what is the variable I used? Okay, w. Okay, don't get confused. Let's say epsilon. So if you see this channel matrix, the size of the channel matrix is nr by nt. So nr by nt in the sense, you will have, as per this application, you will have more number of rows. Okay, you will have more number of rows. So the number of transmitting antennas are 2, you have less number of columns. Okay, so again here to solve this, you can go for least square solution. Okay, you can go for least square solution. Whereas again the same massive MIMO, say this is the base station, these are the users. Let me consider the downlink scenario. So base station is transmitting, users are receiving. So if you see, there are uh, uh, this is the receiver. Okay, so there are less number of receiver antennas, but there are more number of transmitting antennas. Okay, more number of transmitting antennas. You can get the transmitter symbols. In regression problem, regression coefficients you are finding. Whereas in MIMO communication system, we are going to find out the transmitter vectors, transmitter symbols. What are the symbols transmitted from the transmitter? So this can be solved with least norm solution. Okay, so regression is basically a prediction problem. Regression is basically a prediction problem. So I will write one more application here. uh, we have the transmitter, we have the receiver. Between the transmitter and receiver, we have the channel. So usually what happens, we will transmit some pilot signals from the transmitter. We'll receive the pilot signals in the receiver. We estimate the channel. So the channel is fed back to the transmitter using a feedback channel. Okay. So by observing the channel, the transmitter, okay, it goes for different modulation. For example, if the channel is very, very poor, so it won't transmit anything. because even if you transmit, okay, that won't reach the receiver properly. If the channel is okay, moderate, then I will go for BPSK modulation. That means 1 bit per 1 symbol. If the channel is very, very good, then I can go for 16 QAM or 64 QAM or 256 QAM. Like that, I can go for higher order modulation because the channel is good. Whatever I am transmitting, that will reach. But here there is a problem. Okay, you are just sending the pilot. The channel is estimated. Again, the channel information is transmitted to the transmitter using a feedback channel. Now, see the obstacles, the objects moving between the transmitter and receiver, they keep on changing. By the time when the transmitter receives the channel information, okay, the actual channel might have changed. So what we can do, by observing the existing channel and other few parameters, you can predict what could be the channel, what could be the channel for the next transmission. Instead of having the channel for the previous transmission and transmitting the symbols, that may lead to a lot of errors. Okay, you can predict the channel based on the available channel information. Based on the available channel information, you can predict the channel. Okay, so channel prediction. So this is also a prediction problem. So you can use a linear regression concept here. Channel prediction. Once you have the predicted channel, how good your model is, once you have the predicted channel, you can go for adaptive modulation and coding. That means you can change, instead of going for a fixed modulation, you can change the modulation based on the channel. Adaptive modulation and coding. Coding in the sense, I will go for different code rates. If the channel is very, very poor, then I will add more parity bits. If the channel is good, very less number of parity bits. If the channel is so good, don't transmit any parity bits. Like that, I will do. This is one application. Even you may have, okay, multiple antennas. Okay, this multiple antennas, I will just come in the other application. You might have heard about OFDM. Okay, the total system bandwidth, that is divided into number of subcarriers. In each subcarrier, we just, each subcarrier is modulated with a different symbol. So each subcarrier experiences different channel. For example, here if you see the channel is poor. For this subcarrier, the channel is poor. Whereas here it is good. Here it is poor. Here it is good. So each subcarrier experiences independent fading. That is the idea of OFDM. So each subcarrier is modulated independently. So you have to predict the channel. Usually channel is available in the receiver, but the transmission is happening at the transmitter. So at the transmitter, somehow using the machine learning algorithms, if you can predict the channel for each and every subcarrier, okay, then you can do the modulation accordingly. Here the channel is very, very good. So this subcarrier I'm modulating with 64 ohm. This channel is very poor, so I may go for BPSK. Like that, I can decide the modulation. Okay, so there are plenty of applications for linear regression. Is this clear, students? I'm sorry, is this clear, participants? Is this okay? Am I going in the right speed?
Yes, sir.
Okay. Okay. Now we'll start classification. Again, I'm just going to discuss another application of machine learning other than regression. Okay, this binary classification or multi-class classification that comes under supervised learning. So we have the data set. Okay, the same representation. We have m samples. Okay, since this is supervised learning algorithm, you have the feature vector and the corresponding label. Okay, but what is the problem here? So in the linear prediction, we don't have the range. Okay, you have the weights Based on the input, you are going to multiply the features with the weights, and you may get any value that is in the real space. Okay, there is no restriction. You can get any value, but that's in the real space. Whereas in the classification problem, you have set of possibilities. Okay, for example, binary classification. Each output, it can be either +1 or -1, or +1 or 1 or 0, something like that, or it can be 1, 2, 3, and 4. Okay, you have the set of possibilities. Only these values are the labels, whereas in the previous case, okay, you have uh, R space. It can take any value in the real space. Okay, so for explanation I'm just taking a binary classification, but this can be extended for any multi-class problems. Okay, I'm going to discuss a few supervised machine learning algorithms for classification. Then I'm going to tell how this can be used in wireless communication applications. The very first algorithm is K nearest neighbor, or KNN algorithm. K nearest neighbor, or KNN algorithm. This is usually people call this as a lazy algorithm, because this particular algorithm, this won't result in a model. In machine learning, the main objective is we have to create a model. But this particular algorithm, it won't use the training data for creating a model, but it just stores the training data. Okay, it just stores the training data. The concept looks very simple. Okay, say for example, I'm just taking only two features. This is feature one, this is feature two. Okay, two-dimensional, because we can visualize two-dimensional very easily, but practically the dimensions, okay, that's very very high. I'm just using two-dimensional data. So already since this is a supervised algorithm, we know these are the samples and we know the corresponding label. These are the samples and the corresponding labels we know. A new data point comes. Okay, earlier I said we have the model. If you have the model, you can say if it is above the model, it is one, it is category B. If it is below the model, it is category A. But we don't have the model at all. So what we have to do, we have to find out the closest point. Okay, for example, this is the closest point. What is the corresponding label? Okay, what is the corresponding label? I'm just explaining one nearest neighbor. I'm just for the new test point, I'm going to find out what is the closest point. What is the corresponding label? If you see the corresponding label is category A, so automatically this is assigned to category A. You may think that this algorithm is looking very simple, but what is the problem? Say you have a category point here. This is the outlier. A category point here closer to this, but what you may think, this is closer to this point, so you may decide in favor of category B. You may classify this as category B, but actually it should be belong to category A. So what people do, instead of go for k is equal to 1, they go for higher values of k. Okay, so they consider more neighbors. Okay, for all those neighbors, what are the labels? Then they will decide in favor of the majority. And another important thing, usually they go for odd values of k numbers. Say for example, 3, 5, 7, like that. Why not even means, say uh, two two neighbors may say in front of A, another two neighbors may say in front, in favor of, not in front, in favor of B. So the tie cases will occur if you consider even number of neighbors. So to avoid that, usually machine learning engineers, they go for odd number. Okay, you can see here, as I explained in the previous slide, here they took k is equal to 5. This is the new data point. Okay, I'm just looking for 5 nearest neighbors. How do you find out the nearest neighbor? Okay, there are different metrics available in mathematics. You might have studied about equilibrium distance. Okay, if you have two different points, okay, if you have two different points, how do you find out the distance? Square root of x2 minus x1 the whole square plus y2 minus y1 the whole square. This is the distance formula. So you just find out the distance. Okay, then you sort, then you take five minimum data points. So if you see, these are the 5 points that is closer to this new data point. So I'm just looking the corresponding label. This is a, this is a, this is a, these two are b. So there are three A's and two B. I will decide in favor of the majority, that is A. So this is how the new data point is classified. Actually speaking, we don't have the model. Usually what happens in machine learning, once you fit the model, once you have the model, then we will throw away the data set. We don't want the data set anymore. With the model itself, if the new data comes, we will classify whether it is 1 or -1. That is possible. We don't store the data. Once the model is ready, we won't store the data. But here the problem of KNN algorithm is, we have to store the data always. We need to have the data always. Another problem here is, for every new point, for every new data point, what you have to do, you have to find out, okay, the k nearest neighbors. How do you do that practically? How do you do that? So you have to calculate the distance to the test point, distance from the test point to all the data points available. Say I have 10 lakhs, I have 10 lakh records. So what I have to do, I have to find out the distance to this 10 lakh points. So the computational complexity is very, very high here. Even though the algorithm looks simple, the computational complexity is high. I have to find out 10 lakh for every data point. For every new data point, I have to calculate this 10 lakh distance calculations. And I have to store the data. I have to store the data always. And after calculating the distance, how do you know the nearest neighbors? Then you have to sort the data points based on the distance. So if you have m data points in computer science, we know in this big O notation, the complexity is, time complexity is m log m. So if you just take this 10 log points, the complexity, time complexity also goes. So these are the drawbacks of KNN algorithm. Okay, again this k, that is hyperparameter. We don't have the idea whether we have to use k is equal to 1, k is equal to 1, or k is equal to 3, or k is equal to 5, or k is equal to 7. We don't have the idea. So what they do, using cross validation approach, they calculate this k. Using cross validation approach, they calculate this k. What is cross validation? You have the m data points. You have the m data points. For example, say you have 10,000. What I will do, I will take 700. I will split something like this: 700, 300. So this is for training the model, and this 300 for validation. How do I do validation? Okay, what I will do, I have the trained model based on this. Okay, I have the trained model. For KNN, actually, there is no model, okay, that I want to tell, but generally I'm explaining what is cross validation. I have the model. Then what I will do, these 300 samples I will take, I will just check whether the model is above the line or below the line. I will classify it's 1, I will classify it's 0, something like this. All the 300 points I will classify. But we know already what are the labels. So if you see, we have the actual label and we have the predicted label. So you just find out the difference. That means accuracy. How many data points are classified properly? That is actually classification accuracy. So what I will do, for k equal to 1, I will find out the classification accuracy. K equal to 3, I will find out the classification accuracy. K is equal to 5, what is the classification accuracy? So this we will plot. K equal to 1, 3, 5, 7 something like this. Y-axis is classification accuracy. Say it may increase, then again it may decrease. So for what value it is maximum, for what k value it's maximum, okay, that I will consider. So k is basically hyperparameter. Again, here there are some issues. I don't want to discuss too much thing, because if the outliers are more in the validation part, that's also an issue. Okay. So in KNN, we don't have the model. That's the drawback. Since there is no model, we have to store all the information. Okay. So we'll go for a classification algorithm which has a model. Okay. Very first one what I'm going to discuss, that is decision tree. Okay. Already in data structures, you might have studied about this decision tree concept. Almost same idea here. So you have two different nodes. One is decision node, okay, and other one is leaf nodes. So leaf nodes, they provide the labels, okay, they provide the labels, whereas the decision nodes, each decision node it has a question, okay. How the question will be means some feature and some value. Basically, okay, it's something like a feature value combination. Okay, we have two different types of nodes. Decision node, each decision node will have a question, okay, that is associated with a feature and value. Then leaf node, that basically provides the label. Okay, the tree will grow. Again, what is the height of the tree, what is the depth of the tree, that is again the hyperparameter. Okay, so we have to use cross validation, and we have to set this is the appropriate, or this is the proper height required for the decision tree. But what is the concept used here? So here, so already I said, if you take a data point, for example, first record, it may have multiple features. For example, I'm just taking 5 different features: height, weight, or as per our example, age of the car, kilometer run, um, some other things like fuel type. These are the features. So, which feature I will ask? Okay, whether which feature and what is the corresponding value. Okay, whether I have to use f1 or f2, or here in one feature itself different values, what is the value? So that is the complexity here. How many questions we have to ask, what is the depth of the tree? Okay, these are the complexity here. Here they use a simple idea. In information theory, you might have studied about entropy. That idea they use, okay, to identify which question is the best question. Okay, if you see in information theory, you might have seen this plot. When probability is 0, that means the event is not occurring, the corresponding information is 0. When the probability is 1, that means it's a certain event, the corresponding entropy is 0. When it is 1 by 2, you will have the maximum value. Okay, 1 by 2 means we have the confusion. Whether it is 50-50 chance. In that case, we have the maximum information. So the same entropy idea is used, okay, to check, to decide which question is the best question. I can give a very simple example. Say we have 1,000 data sets. I'm just asking a question, okay, some kth feature less than some value. Okay, so what I will have, I will just check before splitting the tree, before splitting this tree out of this 1,000. Okay, how many labels have the probability, how many labels are one, how many labels are one. For example, say out of 1,000 275, okay, they have the label 1, remaining are 0. So I will calculate the probability. Okay, then after asking this question, whatever the data points satisfy this question, okay, they are moved to the left node. Whatever the data points they don't satisfy, they move to the right node. Okay, for example, say this is age of the car. age of the car. I'm just looking if the age of the car is less than 3 years. That's the question. I have 1,000 cars. Say first car age is less than 3 years. Fifth car age is less than 3 years. 75th car age is less than 3 years. Like that for all the 1,000 cars. Whatever fall here, I will write here. Whatever not falling here, I will write here. So again, for each of these samples, we have the label. I will look for the label. Okay, I will look for the label 1, and I will look for the label 0. So I will find out the probability. Say 300 falls here and 700 falls here. Okay, so I'm going to find out the probability out of this 300. How many have the label 1? Similarly here also, out of that 700, how many have the label? So all these probabilities, I will use entropy formula. Here you can notice this is the measure information gain. So what is the entropy of the root node before splitting into tree? What is the entropy of the root node? After splitting, I have two childs now. Okay, ds and d no. What is the entropy of ds? What is the entropy of d no? And this is the weightage. Okay, that means out of 1,700 are yes. Out of 300 are yes, and out of 1,700 are no. Okay, so these are just the weights. So what we have to do, this may be little difficult to understand. So we have to calculate the information gain for each feature value pair. Similarly, this feature and some values, this feature, some values, this feature, some values, this feature, some values. So which question is giving the highest information gain? That is the first question I'm going to ask. So like that, I can keep on increasing the tree width. So here the advantage is you have the model. The model is tree only. Tree is the model. Okay. So we have the tree, we have the model. So no need of storing the training data. Once the model is ready, you can delete the data. You can delete the data set. When the new online data is coming, based on the tree, you can make the decision. So as I said earlier, what is the depth of the tree? How many levels you have to go? What is the best question? All those things are complexity associated with decision tree. Then the next one, okay, naive Bayes. So again, you can see any questions here, participants. Any questions up to this? Anything, or can I continue?
Google Map is kind of like driving a car. So Google Assistant. So what?
So shall I continue?
Yes, sir.
Okay. So I'll just go for the third classification algorithm. Naive Bayes. In probability theory, we might have studied about Bayes theorem. Okay. So for classification, we use the Bayes theorem. Before that, if you notice these features in the previous two algorithms, these features are some numbers. It can be anything. For example, 3 years of car, uh, uh, 5 years of car, 10 years of car, all those things. Whereas if you see in name base, the basic requirement is this feature that is binary. You can have d-dimensional feature, but that should be binary. Okay, that is one important. And another thing is this is basically a probability based model. Okay, uh, in machine learning there are two probabilistic based models. One is generative model, another one is discriminative model. Okay, so in discriminative models, given x, okay, given the data set, what is the probability of occurrence of a particular label? Whereas here we will try to understand how the features has come. So we'll try to find out what is the joint probability of x is feature vector and the label. Whereas in the discriminative model, we don't bother about how the features has come. Here we will try to understand how the features has come. Since this is how the features has come, so that is how the labels are associated. So we will just model the joint probability here. Okay. So Bayes, as I said earlier, we use Bayes theorem for classification. And why the name naive means, okay, why the name naive means, we have several features. For example, we have d number of features. To reduce the complexity, we assume that occurrence of one feature is independent of other feature, but practically this is not correct. Occurrence of one feature is independent of other features. So naive means simple. Okay. So this assumption is made, and we also use Bayes rule for classification. That is the reason this is called naive Bayes. Okay. So these are the important steps in this naive Bayes. The very first one is, as I said, we are going to model the joint probability. You can write joint probability p of x comma y is equal to p of y into p of y by x. So what is the probability of occurrence of a particular label? What is the probability of this conditional given x, what is y? So what we do in first step, we will just predict the label. Okay, we will predict the label. Once you know the label, if it is +1, what we have to do, if it is -1, what we have to do. Once you know the label, you just predict, okay, the probabilities of the feature vectors. Okay, this may little difficult to understand. I'm not writing all the mathematics associated, but I'm just highlighting the major steps. Okay, we have the label. Okay, first we have to predict the label. Once you know the label, you have to predict the probability of the corresponding feature vectors. So if you see in the first step, we are predicting a probability p. So if this says that it is corresponding to class 1, we have some features, d features. Similarly, if it says its probability is 0, the label is 0, not probability. If the label is 0, for label 0, we have some d features. So each feature is associated with a probability. This is a probabilistic model. Each feature is associated with a probability. So this is one probability we have to learn. Here d probabilities, here another d probabilities. So totally 2d plus 1 parameters we have to learn. This is a probabilistic approach. So we have to find out the probability associated with the labels and the features. Once you learn the model, okay, in signal processing, we know maximum likelihood or likelihood ratio test. We will perform that likelihood ratio test. So given the new test data, what is the probability that the label is 1? Okay, if the probability exceeds, if the probability is more than 0.5, I will just decide in favor of 1, or I will decide in favor of 0. Okay, so you can see the likelihood ratio test. Given x test, okay, given x test, I'm just finding the probability. What is the probability that y test equal to 1? Similarly, given x test, I'm finding the probability. What is the probability that y test is equal to 0? If the first probability is greater than the second probability, I will decide in favor of 1, or I will decide in favor of 0. So here, in order to find out this, they use Bayes. Okay, name Bayes. So here the drawback is, as I said earlier, one feature. Actually speaking, the features are dependent, but to reduce the learning parameters, they assume that the features are independent of each other. Okay, that is one of the drawback of this name Bayes. Okay, then logistic regression that comes into the picture. Okay, logistic regression. So earlier I said two different probability based models. One is generative model. We want to understand how the data set has come and how the corresponding label has come. Here it is very simple. I don't want to know how the data set has come, but the given data set, for the given data set, what is the label? I just want to know that. So this model is basically a discriminative model. Okay, I just want given data set whether it is 1 or 0. That only I want to find out. Okay, so again I'm just taking a two-dimensional feature just for visualization, f1 f2. If you assume I know a vector. In the coming slides I will tell what is this vector. I know a vector. If I know the vector, I can construct a line which is perpendicular to this vector. Okay, using the logistic regression model, I know a vector W vector. If I know the vector, I can find out a perpendicular line. You assume that this particular line that classifies accurately. So these are plus, these are minus, something like this. So our aim is we need to find out a vector. If I know the vector, I can know this line, classification line. We need to find out this vector which exactly classifies uh, plus and minus, two different classes. Okay, so how do you enable this? How do you enable this? Say for a new data comes, if a new data comes, what I will do, I will multiply the data with this W vector. If it is greater than 0, this line is W transpose X vector is equal to 0. If you have the data point here, the meaning is you can understand that this is on the line. So we have the confusion that this particular data point, whether the data point belongs to plus or this data point belongs to minus. So you have the probability of occurrence 0.5. So we have the confusion. But if this value W transpose X, if it is more than 0.5, so we can understand that that is belongs to plus 1, more chances, okay, more probability that it is belongs to plus. And if it is somewhere here, okay, less than 0, W transpose X less than 0, less than or equal to 0, so I can understand that there are more chances that that belongs to minus. But here I have written 1 and 0. Practically this is not possible. Okay, this you won't get exactly 1 and 0. You will get some value, for example 0.85, 0.15, like that you will get the values. Okay, so when you do this W transpose into X, you won't get exactly value between 0 and 1. You will get a value, higher value. So, but we have to map the higher value, between 0 and 1, because we need the probability. So what they do, this W transpose into X, that is given as the input for a function. Okay, in neural networks you might have studied about this function, sigmoid function. Okay, you see, if this value is very very small, okay, that is mapped to 0. The y-axis is mapped to 0. At 0, okay, at 0, when you substitute 0 here, t equal to 0, 1 divided by 1 plus e power 0 is 1, 1 by 2 0.5. So when W transpose X, okay, when W transpose X is 0, as I said earlier, when W transpose X is 0, the probability of occurrence, whether it belongs to plus or it belongs to minus, that is 0.5. You can see that. And if the probability of this W transpose X increases, I need to map this to 1. When it is increasing, I need to map this to 1. So what we will do, we have a W. Okay, this we are going to find out. We need to find out a W. If you know the W, you can find out the perpendicular line. Okay, that perpendicular line splits the data points properly. Okay, that is the assumption. So what you have to do when the new online data comes, we have to multiply this new data with this W, and we have to give that as the input of a sigmoid function. Then you will get the value. If the value is greater than 0, if the probability value is very, very high, more than zero point 0.5, we have to decide. Here it is available. If the probability value is greater than zero point 0.5, I have to decide that the label is 1. Otherwise, I have to decide that the label is 0. So using iterative procedure, you can find out the secret W vector. Okay, in the logistic regression, you can find out the secret W vector. So this is basically the step size. YA is the label for all the data points. We are doing this. So this is what the function, okay, for the new test data. This T represents the iteration. So our Tth iteration, this is the weight. Then it is updated T plus 1, T plus 2, like that. This will go. Finally, you will get the weights. Okay. Uh, Finally, uh, so I'll just redraw the diagram. I'll redraw the diagram. So we have in logistic regression, we add the weight vector. Based on this weight vector, we constructed a line. Okay, this line is perpendicular to this weight vector. Okay, so if the data point is exactly available in this line, then we have the confusion whether it belongs to plus or it belongs to minus. Let me draw the parallel lines. Let me draw the parallel lines. Similarly, in the negative side also, I'm drawing the parallel lines. Suppose a data point is available in this line. So I said if it is available in this W transpose X is equal to 0, then the probability is 0.5. If it is available, okay, in the other line, for example, this line is W transpose X, okay, that is uh, equal to 1. This line is W transpose X, okay, that is equal to minus 1. So if it is available in this line, second line, the meaning is the probability is more than 0.5. Suppose if it is available in this line, the probability is less than 0.5. So what I'm going to do, I'm going to use an approach called widest street approach. So I'm not going to use just a line. In higher dimension, these are planes, basically hyperplanes. Okay, so I'm going to move this. I'm going to use a margin for positive. I'm going to use a line or support vector for negative also. Okay, so I'm going to move this line until you capture a data point, positive data point. Similarly, I'm going to move this line to the parallelly in the negative side. When it captures, until it captures one or few this negative data points. Okay, so these data points acts as support vectors. These data points acts as support vectors. So if see, I'm not just going to use a line. I'm going to use this widest street. Okay, so if it is above the street, I'm going to classify this as +1. If it is below the street, I'm going to modify this as I'm going to classify this as -1. Okay, so this is the concept of support vector machine. Here the optimization problem is we need to increase the width or we need to maximize the margin. Okay, we need to maximize the margin, then you will have very less amount of classification error. Okay, so the optimization problem is, so if you solve, this is the width. So 2 over norm W square, this is the width of the margin. So we need to find out a W which maximizes the width. Okay, but there are some constraint. That constraint is When you perform W transpose into X, that should be greater than or equal to 1. So this line is W transpose X, okay, equal to 1. This line is W transpose X equal to minus 1. So if the label is plus 1, then it should be above the data point should be above this line. If the label is minus 1, the data point that should be below this line. Okay, so we need to find out a W which maximizes the margin, and it has to satisfy these two constraints. The same optimization problem, see here I want to maximize. So if you do the inverse, instead of 2 over norm W square, if you do norm W square by 2, this becomes a minimization problem. And these two conditions you can combine and you can write as a single condition. Okay? So this is the optimization problem in support vector machine. There is another issue. You may have some outliers. Okay, say a positive, a data point corresponding to positive, but that may be available in the region corresponding to the negative. So these are outliers. So this is linearly inseparable data. Linearly inseparable data. So how do you handle the outliers? So there is a variant called soft margin SPM. You can see this is the optimization problem we have written in the previous slide. So other than that, I'm just adding a penalty term. Okay, penalty term. That means this data point. Okay, I'm going to add an error so that it reaches this region. Suppose here there is a data point, I'm going to add an error, so it comes here. So for each and every data point, I'm going to add an error. This is called soft margin SVM. So this error, okay, this error should be positive. And if you see other than this, I'm also adding that error term. Okay, so for linearly inseparable data set, we can go for soft margin SVM. This is a variant. So using this, you can address the outlier issue. Any doubts here, participants, up to this? We just started discussing about various classification algorithms.
No, sir. No, sir. You proceed, please. Thank you.
Okay, where is the application? Okay, so presently we are talking about massive MIMO. Okay, so you have millimeter wave communication, massive MIMO, all those things. You have hundreds of antennas. We have hundreds or thousands of antennas. So actually speaking, theoretically the idea is good, but for each antenna you need a RF chain. That means you need a power amplifier, modulator, demodulator, and the receiver you need a low noise amplifier, all those things. So the hardware complexity grows with the number of antennas. Hardware complexity, signal processing complexity, number of RF chains, all those things increases with the number of antennas. So this is the biggest challenge. And we know the fundamental idea that we need to place the antennas with a minimum spacing of lambda by 2 so that each antenna experiences independent fading. Independent fading. So whatever the channel for the first antenna, the same channel will not be there for the second antenna. So some of the channels may be good, some of the channels may be bad. Okay, some of the channels this may be good, this channel may be good. So why to transmit in the antennas which is experiencing bad channels? If you transmit some information in that, again it's of no use. That will be lost in the channel. So what we have to do, we have to identify which antennas we have to select. Okay, which antennas we have to select. That's the problem. So there is a popular algorithm, Euclidean distance based antenna selection. So what they do basically, so H into X, this is the channel matrix. We have the possible transmit vectors. So at the receiver side, otherwise I will go for an example so that you can understand easily. Maybe I'll write here. Say I have a very simple example. I have 4 transmit antennas, but I want to select 2 antennas out of that. So what are the possible combinations? N total, combination NT, which is 4C2, which is 6. So I can, out of 4 antennas, I'm going to select 2 antennas. That can be 1, 2, or 1, 2, 2, 3, or 3, 4, or 1, 4, or 2, 4, or 1, 3. So I need to select 2 antennas. Whether I'm going to select 1 and 2, or 2 and 3, or 3 and 4, or 1, 4, or 2, 4, or 1, 3. Okay. So usually the optimal algorithm is this equilibrium distance based algorithm. So for example, if you take this first 2 antenna, you assume we are using BPSK modulation. So there is a possibility of transmitting +1 and -1. So we have first antenna and second antenna. These are the possible transmit vectors. You may transmit +1 in the first antenna, uh, uh, +1 in the first antenna, and no symbol in the second antenna, -1 in the first antenna, no symbol in the second antenna, or first antenna no transmission, second antenna +1, 0, -1. These are the different possibilities of symbol. Okay, so what I'm going to do, we are going to find out the equilibrium distance. We are going to find out the equilibrium distance of all the received constellations. So here I will find out some equilibrium distance. For this combination, I will find out the equilibrium distance. For this combination, this combination, this combination. Which antenna combination is giving the maximum equilibrium distance? That antenna combination I will select. So you can see, we just plotted some graph, average bit error rate versus various algorithms. This is no antenna selection. So you can see 10 power -4 bit error rate is achieved around 20 dB. Whereas if you go for antenna selection using EDAS algorithm, around I think 13 dB or something, we are getting the same performance. So we have a gain of around 7 dB here. So what is the problem? The problem associated with this EDAS, you just see these are the antenna combinations. If there are 6 total antennas, I'm going to select 4 out of that. If I use this, like QPSK, if I use QPSK modulation, you just see the number of real value multiplications required to execute this algorithm. When compared to other conventional algorithms, this particular EDAS algorithm needs higher computational complexity. So when I started this presentation, I said latency. Okay, that is an important aspect. We need to bring down the latency from 10 millisecond to 1 millisecond. If the computational complexity is very high, then the latency, we have to pay more for the latency. Okay, so even though EDAS is performing well, we cannot use that EDAS. So what is the solution? So here you can use the machine learning algorithms. We have the channel matrix H. First, you have to extract the features. What would be the possible features? Say, for example, I'm just taking a 2 by 2 channel matrix H11, 1, 2, 2, 1, 2, 2 transmitter antenna, 2 receiver antenna. So, absolute value of all these things, this is feature 1, feature 2, like this, all these entries, angle of all these entries. Okay, like this, I can construct so many features for every channel matrix. So using EDAS algorithm, I can execute the EDAS algorithm. If the channel matrix is this one, what is the antenna combination it has to select? Say, for example, 1, 2. Similarly, for the next time, I have different channel matrix. These are the features. What is the antenna combination it has to select? So first, we are just generating the feature vector and the corresponding labels using EDAS. Once we have the model, no need of EDAS hereafter. When the online data comes, I'm going to train the network based on the machine learning algorithms like KNN, decision tree, naive Bayes, SVM, all those things. So they observe the data. So that is going to give a label. You have to use 1, 2. If the channel is like this, you have to use 1, 2, or you have to go for 3, 4. So in the previous case, in equilibrium distance based algorithm, so for every time I need to go for this much amount of computations. Now that is not required. Okay, I have the model. Based on the model, I'm going to directly decide what is the antenna combination I'm going to select. So the computation complexity is drastically reduced, but however, you see EDAS is performing better, but you can see when compared to no antenna selection, these machine learning algorithms is performing better. You are getting a gain, but not exactly 7 dB like this EDAS, we are getting 2 dB, 3 dB like that. So different machine learning algorithms. I'm not going to discuss what is the gain associated with each, but what I want to say, you can effectively use the machine learning algorithms for this classification problem. Even though I discussed the binary classification, this is multi-label classification. Okay, you have different combinations. This is class 1, this is class 2, class 3. So totally there are 6 classes. Okay, this is multi-label classification problem. So this is a hot research topic. Similarly, in 5G and 6G, other than massive MIMO, the spatial modulation is very popular. Spatial modulation in the sense, uh, the antenna indices also convey the information. I'm not going to use all the antennas. As I said earlier, I'm not going to use all the antennas. I'm going to select few antennas for transmission. The selected antennas, okay, the selected antennas convey the information about the transmitted bits. This is the idea of spatial modulation. It comes under the family of index modulation. Okay, it comes under the family of index modulation. So the spectral efficiency of spatial modulation is log to m, where m is the modulation order. For BPSK, m is 2, for QPSK, m is 4, plus log to nt. Nt is the number of transmitting antennas. So at the receiver, my job is I need to identify from which antenna I have transmitted. Say for example, if you have 4 transmitting antennas, I can uniquely represent this antenna by 2 bits. 0, 0, that is mapped to first antenna. 0, 1 is mapped to second antenna. 1, 0 is mapped to third antenna. 1, 1 is mapped to fourth antenna. Say I have transmitted a BPSK symbol. So for BPSK, 1 is mapped to 1, 0 is mapped to -1. So I just transmitted +1, okay, from the first antenna. For example, so how it will be, how the transmitted vector will be. The transmitted vector will be something like +1. I'm not going to transmit in other antenna, so it is just 0. In the receiver, if I get this, okay, I will get 2 information. One is I transmitted from the first antenna. So first antenna, when it is dmapped, the corresponding bits are 0, 0. +1 is dmapped to 1. So these 3 bits are transmitted. Even though I transmit 1 bit, but I'm getting the spectral efficiency of 3. So the spatial modulation is very popular in 5G, 6G. Okay, even in the spatial modulation and antenna selection, you can use the concept of this machine learning algorithms. Any doubts, audience? Any doubts here?
No, sir. Quite good.
Okay. As I said earlier, most of the telecom companies, they started deploying massive MIMO for 5G, but there are various issues associated with the 5G. One is whatever the theoretical spatial multiplexing they are telling in the papers, that is not really achieved. Those numbers are not really achieved using massive MIMO. In from 2009, I remember. Okay, some of the telecom companies like Sprint, they started deploying massive MIMO, but it is not that much effective. So people started thinking about alternatives. They don't want to lose the benefit of MIMO, but they wanted to effectively deploy MIMO. So the concept of reconfigurable intelligent surfaces, RIS stands for reconfigurable intelligent surfaces. So you can see, as per this diagram, I don't have multiple antennas in the transmitter. I don't have multiple antennas in the receiver, but I have a setup like multiple antennas in the environment. Okay, so this can be anything. This can be facades of the building, advertisement boards, or even the shirts, whatever we wear, walls of the building. It can be an unmanned area vehicle, or doors of the car, or toll booth. Okay, so the surface is mounted in such a way that the surface is built with the metamaterials. So each of this element acts like an antenna. Each of these elements acts like an antenna. I'm not going to deploy source with multiple antennas, destination with multiple antennas, but the environment, in the environment, I'm going to have this. So I'm just smartly controlling the environment here. Okay. So what happens? You see, if I transmit a signal from the source, what happens? It's something like a single input, multiple output. Again, from RIS to destination, it behaves like multiple input, single output. So automatically, this looks a MIMO system. Okay, so each and every antenna element, they introduce some phase shift. For example, this particular channel, say it has phase 5K. This particular channel, okay, this is a dual hop channel, first hop and second hop. This particular channel, it is introducing a phase shift of psi k. I'm going to introduce a phase shift pi k plus psi k and a minus. So what happens? I'm just canceling the phase distortion. I'm just canceling the phase distortion in RIS. So you will get a significant gain at the receiver. This is what the idea of RIS. So many of the research organizations, many of the universities, they started working on this RIS. This is expected to be implemented. This is expected to be a key component in 6G, and uh, uh, many of the people already started working on this. So here also, so there are two important use cases of RIS. One is there is a destination, so source is transmitting a signal. Since the medium is wireless, you may get the signal directly in the receiver. Another signal is reflected from the RIS. So both the signals you can make in such a way that, okay, these two signals are constructively added. So what I have to do, I have to adjust the phase in the RIS so that these two signals are constructively added at the destination. There is another use case. You can see this is the desired user, this is some other user. Okay, so RIS is transmitting, so whatever the signal intended for this user, that is also received by other user, that is also received by other user. So what I'm doing, I'm just adjusting the phase in the RIS so that uh, this introduces constructive interference for the desired user, and it introduces the destructive interference for the desired users. This is actually called energy null. So whatever we have discussed, that antenna selection, MIMO, massive MIMO, receiver structure, that regression problem, all those things are applicable in RIS. This is exactly similar to MIMO. As I said earlier, so each RIS element, so this K indicates RIS elements. So there are capital N number of RIS elements. It can be 64, 128, 256, 512, like that. Okay, so each RIS element, it introduces a phase. What is that phase? The phase corresponding to the first half, the phase corresponding to the second half. So I'm going to generate a phase at RIS, okay, which is the addition of these two phases. And I'm going to cancel the phase. I'm going to cancel the phase. So what happens exactly? The phase distortion is going, okay, I will get a huge gain. Okay, I will, even though the signal is transmitted with signal to noise ratio ES by N naught, I'm getting a huge gain at the receiver. This is what the idea of RIS is. But practically speaking, so each and every RIS element, it has to create an angle, it has to produce a phase angle from 0 to 360 degree. But we have the hardware constraint. So the RIS element, practically, even though theoretically the idea is good, the RIS elements cannot produce all the angles. Okay, so whatever fabricated so far, it's something like a on-off switch. So it can produce a certain phase angles. For example, 90 degree and minus 90 degree, or for example, four different phase angles: 0, 90, 180, 270. Okay, so only discrete phase angles it can produce. It cannot produce the continuous phase angles. This is the hardware limitation. So the problem is, okay, so for practical implementation, the concept of discrete phase shifters has come. So here what we are going to do, we know that our RIS is capable of producing only these two phase angles. But by observing the channel, we know what is the phase angle it has to produce. What is the phase angle it has to produce? So what you do, you just find out this phase. Say for example, this phase angle is 120 degree. So this is closer to 90 degrees. So what I will do, I will produce a phase angle of 90 degree. Suppose if it is minus 60 degree, I will produce minus 90 degree. So this is the practical implementation. So if you see, this is the simulation we did. We considered 128 reflective elements in RIS. You just see this one, this yellow color is intelligent transmission graph. One bit means we have two possibilities, either 90 degree or minus 90 degree. You can see the performance. It's not good, as good as the ideal case intelligent. But if you go for more possibilities, 2-bit means there are more possibilities: 0, 90, 180, 270, something like that. You see that 2-bit discrete phase shifters, that is performing better than the intelligent case. So why I'm talking here, you can introduce the concept of machine learning here. Okay, so if you have these kind of phase angles, for example 5k, psi k, okay, so instead of every time using this MMSE estimator to find out the closer phase angle, so if these are the channel gains, or if these are the phase, okay, you can directly make your model so that it will directly produce either 90 degree or minus 90 degree. So basically these are channels. So these are channels. This is another channel. These are channels. So if you, for the given channel, okay, if you know some labels, whether it has to produce 90 degree or minus 90 degree, all those things, you can have the data set. You can create the data set. You can train the model. Once you have the model for the new channel, for the new channel, automatically the model will tell what is the angle it has to produce, whether it is 90 degree or minus 90 degree, like that. Okay. Similarly, another popular concept in 5G 6G is this uh, uh, NOMA, non-orthogonal multiple access. So whatever we have used from first G, we use the concept of orthogonal multiple access. Say for example, in first generation it is FDMA, second generation TDMA, third generation CDMA, in fourth generation and fifth generation they were talking about OFDMA. So here orthogonality in terms of frequency, orthogonality in terms of time slots, orthogonality in terms of pseudo code, and not that pseudo random codes. Here orthogonality in terms of subcarrier frequencies. Now they are relaxing that orthogonality condition. Okay, that's called non-orthogonal multiple access. So for example, if you take OFDMA, we have the total bandwidth. The total bandwidth is divided into subcarriers, and only few subcarriers are allotted for each and every user. So the total bandwidth is not given for each and every user. Only the limited portion of the bandwidth is given to the user. So the capacity of the user comes down. Whereas in NOMA, the entire bandwidth is allocated for each and every user. But the power allocated for the users are different. Power allocated for the users are different. So what they do, usually they allocate, I will take a simple scenario. We have the near user, we have the far user, near user. If you check, this is the channel for the far user, this is the channel for near user. Obviously, we know the channel gain of near user that will be good than the far user. This is one aspect. So in order to give the fairness, because he is also far user is also paying, near user is also paying, so we cannot differentiate in terms of service. Since he is closer to the base station, I am giving better service. That is not the case. So what I have to do, I have to allot more power for the far user and less power for the near user. So we will differentiate the users based on the power allocation. So here you can see some of the equations. Say this base station is transmitting a signal simultaneously for the near user and far user. This is the far user signal. This is the near user signal. So base station superimposes the signal and transmits. But you can see the power allocation for the near user signal and the far user signal, that is different. Alpha NU is the power allocated for the near user. Alpha FU is the power allocated for the far user. So you see the mathematics. I'm not going to discuss much about this mathematics. So usually what happens, this is the signal received at the receiver, at the far user receiver. You see already I said this HNU is weak. The channel gain for the far user is weak. Okay, so the channel gain for the far user is weak. The power allocated for the near user is small. So this particular term is not significant. Okay, so what we will do, we'll try to recover the signal corresponding to the far user. Whereas when it is near user, as I said earlier, this HNU is stronger. Alpha NU, okay, this HNU is stronger. Alpha FU is higher. Power allocated for far user is higher. So what happens? This term is dominant, but we want to receive the near user signal. So first, what we will do, at near user, we will deduct the far user. Then we will remove the effect of far user. We will remove the effect of far user using successive interference cancellation. So this is what the residual signal. Then we will deduct the near user signal. This is what the idea I just explained for a 2-user case. So you can imagine for multiple user case. Okay. So I just want to tell that you just see this is the data rate, some data rate for 2 users. If there are 2 users, what is the data rate of user 1 and user 2? For example, if this is the data rate of user 1, you see the corresponding data rate of user 2. If it is NOMA, you see the corresponding data rate of user 2 is very, very high. Okay. So I just want to tell the machine learning aspects here. Here the problem is we need to maximize the sum capacity, the data rate achieved by the near user and far user. The total data rate we have to maximize. So we don't have the control on the channel because the channel is random, but we have the control on the power. Okay, what is the power allocated to the near user? What is the power allocated to the far user? We have the control. So this becomes an optimization problem. We need to maximize the power so that the capacity is maximized. We need to find out the optimal power so that the some capacity is maximized. So there are some constraints. The data rate achieved by the near user, that should be more than some value. Similarly, the data rate achieved by the far user, that should be more than the QoS demand, and the total power alpha nu plus alpha n fu, that should not exceed unity. That should be equal to unity. It should not exceed unity or less than unity. So every time the channel HFU and HNU, that is random. So every time you have to calculate this alpha NU and alpha FU. So instead of that, what you can do, you can go for a data set generation, okay, and you can find out what is the optimal power. If these are the channels, this is the optimal power. If these are the channels, this is the optimal power. Like that, you can create a data set. Okay, once the data set is ready for the new channels, it will automatically allocate the power. That is what I want to convey. So whatever we have discussed here, that is ordered NOMA, fixed NOMA. That means the decoding order is fixed. First we have to decode the for user, then we have to decode the nearer user. Then there is something called ordered NOMA. Here the decoding order is based on the channel gains. Okay, the weaker user is decoded first. Okay, so again the decoding order, how we will decide the decoding order. So there also you can use machine learning algorithms. Okay, which user you have to decode first. Okay, I just took very simple example, only two users, but practically you just understand the number of users are very high. So which user has to be decoded first, which user second, like that. Okay, uh, computation is very difficult. So you can use machine learning algorithms here. Okay, so I just added another graph. You just see if it is optimal power allocation NOMA, you can see this red color. The sum capacity is higher when compared to the suboptimal capacity. But if I combine this reconfigurable intelligence surface and this NOMA and the optimal power allocation through machine learning algorithm, you can see the sum capacity. So that's very high. This is much far when compared to this the NOMA alone technique. Okay. Finally, I just want to touch uh, unsupervised algorithm. uh, uh, K means clustering. So here also we have the data set. For example, first record, second record, like that we have m records, but we don't have the labels. We don't have the labels. So we cannot classify, but based on the features, we can group these data sets. We can cluster these data sets. Okay, so you can see this is the data point. For each cluster, you have the centroid. Okay, so we need to associate. We need to put each and every data point in some cluster. For example, we have k clusters. K can be 4, K can be 5, K can be 100. Okay, so the minimum value of K is 1. 1 means all the data points are put in one cluster. The maximum value of K is the number of data points. Say if you have 1,000 data points, each data point you can put in one cluster. Each data point is a cluster. So maximum you can have 1,000. Okay, I'm not going to discuss how we have to set this K. But for a given K, we know K is 3 or 4. Okay, so you have to find out the median values. Okay, after mapping a data point, I'm putting x1 here, x2 here, x10 here, something like this. So there are so many data points. What we have to do, we have to calculate the distance to the median. Then you add all those distances. So the combination, the cluster combination, which gives the minimum sum distance, that's the best one. Okay, in computer science, they call this as NP hard problem. This is very difficult to implement. To implement. So we go for a simplified algorithm called K-means algorithm or Lloyd's algorithm. So this K value is given to us. So in the data set itself, you take some k values randomly. Okay, in the data set itself, you take some k values randomly. You can see the figure, you can understand this very easily. Okay, then based on the random, okay, so these are the random clusters, not the correct clusters. So you just find out a centroid. You just find out a centroid. Okay, then what you do, you again check. Okay, you take this point, you take this point, whether you just find out the distance to this centroid, you find out the distance to other centroid. I'm sorry, this is the other centroid. So if this data point is nearer to this centroid, you just associate this data point to this centroid, or you move the data point to the other cluster. Like this, I have to do for all the data points. So randomly, we are selecting few data points as the centroids. So initially, some are associated with those clusters. What I'm going to do, I'm going to find out the distance. For example, this point to this centroid, what is the distance? This point to this centroid, what is the distance? So I feel that this particular point is closer to this centroid, so I'm just keeping as it is. Say I have another point here, I'm calculating the distance to this centroid, calculating the distance to this centroid. This is closer to this point, so I'm just moving to other cluster. So I'm just forming new clusters. I'm just forming new clusters. For the new cluster, I'm finding the centroid. I repeat this procedure. I have to repeat this procedure again and again until any of this condition is satisfied. For example, no new centroids are formed. No data points are moving from one cluster to another cluster, or maximum number of iterations are reached. So if any one of the stopping criteria is met, okay, we can stop this algorithm. Okay, so where this is exactly used. So if you consider the mobile network operators, okay, they have to deploy the base station, relay station. Nowadays in 5G and 6G, they are talking about ultra dense networks. Not only the base stations, we can also have microcell, picocell, femtocells, all those things. So we have to cover the entire area with the different types of networks. That is actually ultra dense networks. So where you can exactly place, okay. So for example, these are the users. These are the users. So we know the data rate demand of each user. We know the coverage ratio. So what we will do, these are nothing but the data points. These are nothing but the data points. You can take few data points as in our application, the mobile users. The users are something like data points. So we will take few users as few users location as a centroid. Okay, what we will do, we'll just check for each user. We'll find out the distance to that place, uh, to other centroid, to other centroid. So the same k-means algorithm we will execute, and we will just find out a user's location. Okay, using this k-means algorithm. So already the operators, they might have selected few locations as the candidate locations. We'll choose, okay, we'll choose that location for placing the base station. That base station can be anything. It can be a macro cell, it can be a micro cell, it can be a pico cell, it can be a relay node. We can go for anything. This is one idea. Another one, in wireless sensor networks, we need to select the cluster heads. So the cluster members has to communicate to the cluster heads. Cluster heads has to communicate to super clusters. Then it has to go to the sync. So how do you form clusters? You can also use this k-means clustering to form the clusters. So in machine learning, these are the data points. In this UDN deployment, these are the users. In wireless sensor networks, you just imagine that these are the sensor nodes. So which sensor node should act as this centroids are nothing but which sensor node you should be the cluster head. Okay, what are the features? The remaining energy, centrality parameter, distance to the cluster head. These can be the features. Okay, you can map this problem to wireless sensor networks also. Okay, so these are some of the references I referred to make this presentation about this machine learning. I just took some online tools. These are some of the papers for this uh, clustering, uniform clustering for ultra dense network deployment. This is the base paper. Reconfigurable intelligent surface. I just took this Basar and Emil Bijarson's papers. Aditya Jagannathan paper for this NOMA. These are the machine learning based antenna selection works. Okay, and to study the fundamentals of machine learning, I just referred this particular book. Audience, you can ask your doubts.
Good morning, sir. This is Dr. Velmani. One small question. Is it
Yes, sir.
possible to apply K-means clustering for mobility network, dynamic network? As you said in previous slide, we can apply for wireless sensor networks.
Wireless sensor networks. Uh, Yes, sir. But the thing is, what is the problem? Since you may assume that the nodes may follow some mobility pattern, something like a random waypoint or a Manhattan mobility model, something like that. So the problem is it won't converge so easily. I think you are understanding what I'm telling.
Yes, sir. Yes, sir.
So you have to limit at certain iteration. It won't converge so easily. So every time you have to change the cluster heads, clusters, all those things.
Yes,
So that
cluster
is the
heads we
reason.
have to rotate it
Yeah,
for
we have to
energy
rotate.
even distribution.
Yeah, so that's the issue associated. But there is a solution for this nowadays in WSN papers. If you see, instead of the nodes moving, you can have a mobile sync. Something like sync is available in UAVs. So those UAVs will move nearer to the mobile nodes and they will collect the information from the cluster rates or the sensor nodes, something like that. There are some papers.
Yes,
But
sync mobility since.
yeah, sync mobility instead of the nodes moving, you can think about it. But as I said, the convergence will be a problem here. Even the paper whatever I was discussing in my presentation, they just assumed the stationary uses. That's the assumption. That is the biggest assumption they made. The users are stationary.
It is for static network.
Yeah, static.
Okay, sir. Thank you, sir. Thank you so much.
Yeah.